meanings. Either you know all the things, or alternatively, 23 only. Is it? Why so less? I was expecting 30 plus. Uh-huh. Oh, I see. Okay. Oh, this is news to me. Okay. Anyway, then let's start. Let's not waste time. As I have wrote that mail that since now that you will be coming to the class, but this thing is not that organized. So I thought that I will take this as as a preparatory class so that I will explain the background of this experiment. As you know, I do every time. I don't know whether I have taken your class earlier. So we used to explain the thing, and then you will come in the lab, and then you will, of course, perform the experiment where you will see all the things. So that's the purpose. So let's start straight away. Yeah, now I feel see 19 students joining, so that's fine. Okay, so now let me come. Okay, what happened? Okay, so now it should come on your screen. You just tell me whether it is there. Yeah, good. So now I go to this presentation and now make it full screen. Is it now? You can see it? Full screen? Okay,
Yes, sir.
right. So now I'm going to explain this one because this is the first experiment you will do in the high voltage lab. There is another experiment. I don't know how it has been distributed. That I have no idea. That the lab committee or somebody knows. So I presume this is the first one that you will do. So what is this? You can see the title. Impulse, withstand and flashover test on porcelain pin insulator. First of all, I have to tell you one thing that you can always ask me a question. What is the purpose of this test, doing this test? Why you are doing it? If you don't do it, what is the loss? Well, first thing that in your life you will learn later on that whatever you do, whether it is a software, whether it is a hardware, whether it is an equipment, it will be accepted by your customer only when it is tested properly. Software is also not accepted without testing. Please remember this one. There is a very, very stringent rule for software auditing. So customer will audit the entire software and then only they will take it. Otherwise, they will not pay. Similarly for hardware. So let's say I am manufacturing a porcelain pin insulator which will be used in the high voltage line. But as you can clearly understand that if this pin insulator fails, then the line will have a fault. So there is a big question on the reliability of the line depending on the reliability of this pin insulator. So then how do we estimate or how do we judge this reliability? The answer is straightforward that we have to perform some tests in the lab. So one type of test is called routine test. Routine test means some of the test which will be done on each and every item. Say for example, what is the leakage current flowing? That's a routine test. Some of the tests are called the type tests. We also call it acceptance test, which means this test will not be done on 100% of the product. Say, for example, you have 1,000 insulators. Done on 1,000 insulators. Whereas routine test will be done on all 1,000 insulators. Type test will be done on only a few of the products. What is typically done in the industry that customer and manufacturer, they will just mutually agree that let's say we'll do it on 5 out of 1,000, and then customer will arbitrarily choose any 5 items out of that 1,000, and then test will be done. If the products pass in the acceptance or the type test, then only customer will accept that product. So it's very, very important. If it fails, then that 1,000 piece insulator customer will not accept, they will not pay. So the company will be incurring big financial loss. So impulse, withstand, and flashover test is a type test or acceptance test, and every product which goes through this test has to pass it. So we are trying to teach you the importance of this type of type test or the acceptance test. Well, all of you may not be working in this area later on, but definitely some of you will work. So it's always very good that you know what is done in industry. So this is straight away related to our industrial practices. So what is the objective that we are going to do today? One is to carry out dry impulse withstand voltage test on 11 kV pin insulator. And you know that every test is done as per certain standards. And this test is done as per Indian standard 731. And if all these standards are always associated with an year, that is the year of publication. Secondly, we'll determine the 50% dry impulse flashover voltage of 11 kV pin insulator, again as per IS 731. Now, you can ask me, or I would like to explain here, that if you look at the title of the test, you see dry impulse withstand voltage test. In other case, dry impulse flashover voltage test, like that. So there are three terms here. One is dry, one is impulse, one is either withstand or flashover. Now, here is a slight explanation required. These are outdoor insulators. So this pin insulator has to work under dry condition, under rainy condition, we call it wet condition. So the tests are also done either in dry condition or in wet condition. Now, then you can ask me how you do the wet condition test. Well, you have to have in your lab what is called artificial raining apparatus. And we also have in our lab, Jadavpur University lab, artificial raining apparatus, where we simulate the rain with the help of a lot of nozzles. And then we put the insulator in that artificial rain and perform the test. So we always have to specify whether it is a dry test or it is a wet test. Next is the applied voltage. That could be impulse, that could be AC, that could be DC. All three is possible. So you have to specify. So today we are going to do impulse test. So we are saying dry impulse test. But that is not enough. Again, for any insulator, there are two types of tests. One is called impulse withstand test. That means there is a voltage already specified, X kV, in the standard. And we have to find out whether the insulator is able to withstand that voltage. So that is called withstand test. Alternately, this insulator will have flashover if you increase the voltage. So we can determine the voltage at which that flashover occurs. So we have to specify whether it is a withstand test or it is a flashover test. Therefore, uh, uh, therefore, we specify it is dry impulse withstand voltage test or 50% dry impulse flashover voltage test. Now 50% I will explain later on. Now for this test we will require an impulse generator, Now, in your third year class, impulse generator was there in your high voltage engineering course. Well, you might have forgotten it. So, let us just, or rather, let me explain it, that what we generally have in an impulse generator. Typically, we have a capacitor, which we call the source or the stage capacitor, and this is being charged over a charging resistance. Once and when it is charged, the sphere gap is open. It is acting like a switch. This sphere gap is nothing but a switch. So we charge it up to a voltage V, and then at a particular instant of time, we switch on. That means the sphere gap breaks down. The moment it breaks down, this capacitor discharges through this resistance. And so if I measure the voltage across this RE, when the sphere gap is open, the voltage across RE is zero because it is earth. One terminal is earth, other terminal is open, it is zero. The moment it switches on, the voltage of the across RE immediately rises to VDC. But then the capacitor discharges through RE, so we get a pulse. So therefore, we can have a particular wave shape. But now, in an impulse generator, slightly, we need more. What is that? In the previous slide, when this capacitor switch is on, the voltage immediately rises to its peak. But as per Indian standard, the impulse voltage should reach the peak value at 1.2 microsecond. So there is a question of controlling that rise. So how do we do it? The circuit is typically like we have the stage capacitor here in the box. Then we have that voltage multiplier circuit, if it is a multi-stage generator. Then when this flare gap fires, then this source capacitor charges the CB, which we call it load capacitor, over a resistance RD. So the charging of CB is controlled, that is the time constant is controlled by RD, and we adjust it in such a way that the peak value across CB, that is the measuring point, is reached at 1.2 microsecond. And then up to what point CB will be charged? Very clear. When this source capacitor is charging CB, it is losing charge, so its voltage will decrease. CB is gaining charge, so its voltage will increase. So at one point of time, their voltage will be equal. And that is the peak value. Peak value of what? The voltage across CB. After that, both the condenser, that is the source condenser as well as CB, they will discharge through RE. This is a parallel path here. So this is a discharge resistor. And by controlling the RE, we can control the discharge time constant. And we know that the discharge time constant should be such that the voltage from the peak value drops down to 50% of the peak value by within 50 microseconds. Now there is a control room where we have a variac by which we vary the low voltage. Then we control the sphere gaps. That means the gap adjustment, because we need the gap adjustment to fire at different voltages. Then there is a trigger switch. Trigger switch means we press the switch when we want to trigger the sphere gap at a precise voltage. And then we have a decimeter to measure what is the voltage at which the capacitor is charged. So this is the control room, which you will see later on, that this is the control panel. And what it controls? First, we have the variac, as I said. And you can also, yeah, you can see here the two bar, these are the rotating, these black ones at the bottom. Then gap control push button switches, that we increase or decrease the gap. When you push these switches, there is a motor operated mechanism by which the gaps increase or decrease. So here are the push button switches at the bottom. Then trigger push switch. So there has to be a switch by which we apply the trigger pulse so that the gap fires at a particular voltage. So that is also here. So that's what is shown here. So now here it is, you can see all shown in details. That right bottom is the variac. So when we vary this, we vary the input voltage. Then we have the two push button switches for decrease or increase, means it is increasing or decreasing not the voltage but the gap distance. Then we have the trigger button here, small one in the middle. Then the DC meter at which we get an indication that up to what voltage the capacitor has been charged. Now comes the DC charging stage. In the DC charging stage, we recall our knowledge of the voltage doubler circuit. In the voltage doubler circuit, what was there? We have the high voltage source. Then we have one capacitor and two diodes, and then one more capacitor, C2. So in one half cycle, C1 gets charged. In another half cycle, C1 in series with the source voltage charges C2 over the diode D2. So in the one half cycle, D2 is not conducting, shown by the red cross. So D1 is conducting. C1 is charged up to the peak value of the source voltage, Vm. Then in the other half cycle, D1 is not conducting because it is reverse biased. So it is red cross mark. But D2 is conducting. So now C2 is being charged by whom? By the source voltage plus capacitor in series. So what is the total value? Or the highest value is summation of these two, which is 2 Vm. So C2 is charged up to 2 Vm. That is the concept of the voltage doubler circuit that was also there in your third year class. So exactly what is the circuit that we use in our laboratory? This is this one, where our maximum output possible is plus minus 175 kV DC. So we have this variac, which I have already shown in the control room, that variac is there. So it's an auto transformer. From the variac, this variable low voltage goes to the high voltage transformer. Its output is approximately 82 kV RMS. Then we have the first capacitor, which is the voltage doubler circuit first capacitor. That means here the C1, you can see it is in series with the source. That is here C in series with the source. This R is nothing but the charging resistor. Remember, any capacitor you should not charge without a resistance in series, because capacitor uncharged condition is short circuit. So you have to put a resistance in series. Then you have D1 and D2, which is similar to the Cockcroft-Walton doubler circuit. So these are D1 and D2. Then what are these switches? Well, this is very simple. By this switch, the diode connection is simply reverse. That means in this one, the diode will be simply reverse connection. So that in one connection, the diode will, say D1 will conduct in positive half cycle, in another connection, it will conduct in the negative half cycle. Accordingly, the C1 will be charged either right side positive, left side negative, or right side negative, left side positive. So then C2 will be charged either top positive, bottom negative, or top negative, bottom positive. So the output, we always say plus minus DC. That's what we do. And that is being done by this toggle switch. This is actually, technically its name is SPDT switch. Single pole double through switch. Single pole double throw switch. Yes. Yeah, yeah, yeah. See, 82 into root 2, that is the big value. And then that into 2, that is your 31. But actually, you can go up to 230. But you know that we never go to the 100%. That engineering never works like that. That is a very important thing you have to remember. We should not go up to the maximum possible constraint. You have to always keep something in your hand which is called a safety factor. This this you should never underestimate, that safety factor. So if the possible is 230 kV, we know we don't go up to 230 kV. We work with a 10%, 20% safety factor, so that even if something happens, some over voltage happens, it is still within my maximum possible limit. Yeah, but this is, remember, the safety factor is so important in our engineering design. Everywhere it is required. Fine. So then you can, from this circuit, you should ask me another question, that where is this? Here you see there are two capacitors, C1 and C2. Where is the second capacitor? Can you see here? No. So where is the second capacitor? The answer is actually from that right hand side. Now you can see that this goes to the multiplier circuit. So all the capacitors are there. That is C2. Then what is this resistance and other things here? Well, these are the measuring one. See, bottom you have a measuring resistance, and then we have a meter which will be calibrated in terms of high voltage, the bottom one. Then you can ask, what is the top resistor? It is an earthing resistor with a plunger type arrangement. Now, this I just explain for the sake of engineering. See, high voltage, when we have so many capacitors, even if you switch off, do you think all the capacitors will immediately discharge all the charge? No. And if by mistake you touch it after switching off, it's not safe. You can have serious electrical shock. So what is there is there is an automatic earthing system. That means even if you by mistake do something, there will be an earthing. What is that? That is an electrical plunger. That means the moment you switch on this low voltage side, the same supply comes here to this plunger and the rod goes up. This is an electromagnetic pull. This rod is earthed, you can see here. And the moment you switch off, this supply is off. So then this rod falls by gravity. Then immediately touches this earthing resistor, and that is connected to this circuit. So the circuit is automatically earthed. The stop circuit. So it's an automatic earthing which gives the protection that even if by mistake I have forgotten something, but earthing will be there. And when once it is earthed, means you are giving the capacitors a path to discharge its charges. So when we are working with at that high voltage level, please remember it is completely different from working with a 100-volt circuit. We have to take all sorts of safety and precautionary measures so that nothing serious happens. I know in one of the very renowned institute, high voltage lab, there was a serious accident occurred just because of the simple reason that they forgot to earth the equipment. And then somebody touched it, and he was in ICCU for almost 1 month. That I know from my personal experience. So we take all this sort of precaution. So now this is the actual photograph that is in the lab. This is the transformer. Which one? This 82 kV RMS transformer. This one. That is on the right side. Then the earthing arrangement on the top. Here you can see the electrical plunger. This cylindrical thing, and the rod is there. You can see here. That is this one. This top one. This earthing resistance plunger and then earth. That is here at the top. Then this is C. Which one? This one here in series with the transformer. So you can see this C is directly, you see it is series with the transformer. Then these two cylinders are the rods here. Here you can see diode. One this side, one on the other side. Then you can ask me one question, that how you change the switch? Well, these are not simple switches, right? You are working at 175 kV DC. So here is a very interesting arrangement. When you come to the lab, you should see it, that this rod, this is connected to earth here. There is another rod on this side which will be connected to this vertical. In another polarity, we just simply rotate this by 180 degree. This rod, this angular rod, it will touch the vertical one. The other side will then go to the earth. So that way, this these two switches, this will work here. So this is very interesting to note, that how the mechanically these arrangements are done. Now we need this arrangement because it's a very high voltage circuit. Then comes the multiplier circuit. And the multiplier circuit, as explained typically in books, that we have 8-stage generator in our lab. So there will be 8 capacitors. Here you can see 1, 2, 3, 4. You can count up to 8. There are horizontal row of resistances. The top one is typically called charging resistor. So when we charge these capacitors, you can see 175 kV on the left. This is coming from that DC charging. And all the capacitors are charged in parallel through these charging resistors. You can see they are all charged in parallel. So when they will be charged at 175 kV, it will be all 175 kV. Or if we charge it up to 50 kV, they will be all 50 kV. After that, during the discharge, we have a lot of options. One, we can have all of them in parallel and then discharge. In that case, you will never get more than 175 kV as output. Second, I can take 4 of them in parallel, connect the 2 group in series, then 175 plus 175, we will get 350 kV as output, as is shown in the right side. This is. How do you do this series connection? By 2 sphere gaps. You can see here. Stage 4, there is one sphere gap. Why stage 4? Because this is the 4th condenser. And then last one, there is one sphere gap. So what do we do? So when this stage 4 sphere gap fires, the top of this capacitor, which is say positively charged, is connected to the bottom of stage 5, which is negative. So that means this first parallel group of 4 capacitor is connected in series with the second, that is the right side 4 capacitor in parallel. So you get 175 plus 175. In this way, I can have 2 capacitors and then 4 groups connected in series. In that case, this sphere gap will be in the stage 2, which is here in stage 4. And I can have all 8 in series. In that case, the sphere gap will be in stage 1, straight away stage 1. And then in the output side, we will have a very straightforward circuit, that means CV, that is shown earlier in your diagram, the RD and RE. So this is called the wave shaping section, which is exactly same as the single phase circuit. What is changing is this multi-stage section, where we can have series parallel combination, and thereby we increase the voltage level, and that's why it is called voltage multiplier section, as you can see here in the middle. So here multiplier section has been already told, that all capacitors in parallel, output will be 175 kV. 4 capacitors in parallel, therefore 2 sets in series, output will be 350 kV. 2 capacitors in parallel, 4 sets in series, so output will be 700 kV. All 8 capacitors in series, output will be 1400 kV. And impulse is always in terms of peak value, so we are talking here about the peak value that is possible. This is the impulse generator of our lab, where you can see these are the sphere gaps, This is a very interesting arrangement. You come to the lab and see that how brilliantly through mechanical arrangement these sphere gaps are controlled. Just look at it. It is a very beautiful engineering. This is Siemens make really good engineering. These are the stage condensers in the vertical columns. Between these corona rings, you can see the black ones. The smaller one is the capacitor, the bigger one is the insulator. So every column has two such smaller ones, so two capacitors. So four columns are there, so eight capacitors. Then you can see diagonally these rods, these are the resistors. So these capacitors, you can see they are connected by charging resistor as well as the discharge resistors. So this whole thing is just like a DNA, helical DNA structure. So one capacitor, another capacitor, they are beautifully connected. So this is the wave shaping section that I have already told. What is there? This is the wave shaping section. That means this is the output bus. What is output bus? If you look at it, this is the top of this multiplier. Here you can see the top of the multiplier. This is the output bus, this one. Then from there, you have CB here, and we connect it by a vertical rod. So we can put a resistance here that will act as RD. Then here you can see another vertical rod connected to a resistance. It is RE. Now, what I impress upon you from the engineering point of view, that look at this. These are very, very big items. So this RE, it is such a big resistance and not a big one, also such voluminous, because this RE will have to withstand the full voltage at the output of this multiplier. That's why it has to be a very pretty big resistance, not a small resistance. And that is the important part of the high voltage design, that these components are not smaller components. And finally, we have the measuring sphere. So this is the sphere gap. So two spheres horizontally, diameter is 25 centimeter, and there is a gap in between. What is there in the gap? Atmospheric air. So let us explain that how do we now calibrate the impulse voltage generator with the sphere gap. For that, we have a standard called IS 1876. Here, the breakdown voltage of the sphere gap is given. Now, if it is 25 centimeter dia and the gap distance is 1.4 centimeter, the breakdown voltage is 42.9 kV peak, as you can see here. Now, you can say that 1.4 kV, so 30 kV peak per centimeter, so 1.4 into 30 kV, I can get a value. Yes, theoretically possible. But in our actual life, we never go by such connection. So what we do? We do practical tests, experiments, multiple experiments, and then we ultimately arrive at a value. So these values are all determined through multiple experiments over the different time to ultimately converge to this value. So in your experiment, you will do it with 1.4 centimeter gap, 25 centimeter dia, so 42.9 kV peak. But that is not enough, because this is also at standard temperature and pressure. And in the lab, on a particular day, temperature pressure could be different. So what is I was talking about now, that 50% value. So the voltage at which the probability of breakdown of the sphere gap for a particular gap setting is 50%. Now, this value coincides with the peak of the impulse voltage. Now, why? You can ask me, why is it so? Now, there is a very clear-cut physics behind that. See, air gap breakdown has been studied very significantly in the lab, and a graph can be plotted which is called voltage time characteristics. So this is the dotted line, and this is the impulse waves. And impulse waves have standard wave shape. Peak value will always rise at 1.2. So you can, if you look at these impulse waves, each one has peak at 1.2 microsecond, and gradually the peak value is increasing. And this voltage time characteristics, this is cutting the impulse waves at different points. And every impulse wave is applied to the sphere gap multiple times, and it is noted how many times breakdown has occurred. Say I apply 100 times, how many times breakdown has occurred. So it has been found that if 50, the value of the impulse, right, the peak value we measure, that value, if it is coinciding with the 50% breakdown, then this dotted line cuts the impulse wave at the peak. I repeat, it is like that this dotted line is done by experimentation, and this impulse magnitude we change by controlling the voltage, and we note down by applying say 100 times or 50 times how many times breakdown occurs. That is called the probability of breakdown. And it can be seen that if it is 50% probability, then this dotted curve cuts that particular impulse wave at the peak, which means that 50% probability actually indicates the peak value. If it is higher than 50%, then we can see it cuts it on the front. That means then breakdown occurs on the wave front. If it cuts, or if it is less than 50%, it cuts on the tail. So breakdown occurs on the wave tail. But now a big question comes that if I apply it 10 times, then it is possible that 5 times breakdown occurs, 5 times breakdown doesn't occur. But if I apply 100 times, is it possible that I get 50 times breakdown, 50 times not breakdown? The answer is no, it is not possible. So then there will be a question of tolerance. That what is my tolerance then? But that tolerance has to have some scientific basis. For that, another experiment was done that if you take the different voltages, like here you see, V10 means 10% probability, V40 means 40%, etc., etc. And if you plot this curve, then this looks like this, and it is called S curve because of its shape. But this S curve, this rising part is very sharp. And this 50%, you can see it is at the middle. Then if I take 40% probability, and if I take 60% probability, and if we drop down on the x-axis, that is V40 and V60. That is V40 means 40% probability, V60 means 60% probability. We can see that this range V40 to V60, because of this very sharp rise, will be within plus minus 3%. And this plus minus 3% is internationally accepted tolerance of an impulse test. So therefore, we will say that the 50% breakdown does not mean exact 50%. We will allow anything between 40% to 60%. So that means if I apply 100 times a voltage, 40 times breakdown is allowed up to 60 times breakdown, but it not 61 or 39. This is called the 50% disruptive discharge voltage. This is the term we use, 50% DDV. But now the problem is with the temperature and pressure. So if the temperature pressure is different in lab condition, then we have to incorporate the correction factors. What are these? So as I have told that for the 25 centimeter sphere dia and 1.4 centimeter gap distance, the value as obtained from the standard is 42.9 kV. But then we have to apply the correction factors so that I get this voltage at the lab condition. And these correction factors there are procedures of determining this. So how do we calibrate it? We connect the 11 kb pin insulator under test in parallel with the measuring sphere gap arrangement. Why do we do that? Because we want to calibrate the impulse generator by including the capacitance of the insulator. Because the insulator will be connected in parallel with the output. Sphere gap is also in parallel with the output. So if we don't put the insulator in the output, then that capacitance is removed from the circuit, so it will change the calibration. We don't do that. We put the pin insulator in the circuit and do the test. Now, how do the pin insulator will be mounted? There was an experiment in the third year of yours. So exactly same thing we do, that there will be a conductor on top of the pin insulator. What will be the length of the conductor? Minimum 2 meter, which will be extended 1 meter on both the sides, or 1.5 times the height of the insulator, whichever is larger. But typically 1 meter is the case. So we take a 2 meter conductor extended 1 meter on both the sides. So this is typically, you can see the right side, and the left side is the actual case where you can see the pin insulator and the conductor is running. But we cannot have such a long conductor in our lab. So what we do, that this metallic structure is actually representing this tower. This horizontal one is representing the cross arm. Now, actual height of the tower is very high, but in the laboratory, we put it greater than equal to 1 meter. Why? Because the capacitance to earth means the general earth, that is the important parameter. So, experiments have been done that if we increase the height of the pole, how much is the capacitance changing? It has been noted that if the height is more than 1 meter, then capacitance hardly changes. Which capacitance? Capacitance to R. So we take this metallic structure of height greater than equal to 1 meter, but not less than 1 meter, because capacitance remains constant when the height is greater than equal to 1 meter. Then we put the pin insulator exactly like in the practical case. And then we put this 1 meter on both the sides conductor. But then there is another important point. You can see the left side that the conductor is running perpendicular to the cross arm. So in the lab, I can put this conductor in any direction, but that is not correct. We have to put this conductor perpendicular to the cross arm. So that's the exact circuit that, this is the generator. Then this is the measuring circuit and pin insulator in parallel. Now what we are going to do, that we know that the sphere gap is going to break down at say 42 point something. And we are using the 2 times multiplier stage. That means output will be 2 times the input. So if I apply 25 kb at the input, the output is expected to be about 50 kb. But there is always a system efficiency, so it will drop down. So we'll adjust the variac and we'll observe the DC meter, let's say at 25 kb. So we'll adjust, we'll read 25 kb and then we trigger. The moment it triggers, the impulse goes to the output. And how we observe it, if you are in the lab, you can clearly see that there will be a big discharge of the sphere gap. It is very easy to see that the breakdown is occurring. So we trigger it by pushing the switch from the lab, and then impulse is applied to the sphere gap. But I want 50%. So what we do, we apply some 4 to 6 times the voltage, say 25 kb, and I find the probability is 70%. So immediately I know that the peak value is higher than the required value. So we reduce the voltage a little bit. How do we do that? By reducing the gap, the sphere gap. Because now it will break down at a lower voltage. So the output will be lower. So this is a complete trial and error. There is now no optimization here, trial and error. We slowly adjust the gap and then achieve what is called the 50% breakdown. So this is all, actual case where the breakdown will take place. So here it is shown that, so let's say 10 times at 25 kV. So observe 10 sparks in multiplier. The measuring sphere should fire 4 to 6 times. That is the 40% or 60%. If the measuring sphere fires less, that means now the peak value is less than the required value. So increase the DC voltage a little. That means increase the gap also a little bit and fire 10 times again. If the measuring sphere fires more than the 60%, then decrease the DC voltage a little bit, reduce the gap distance a little bit, again fire 10 times. So in this way, just through this trial and error, we have to find out exactly at what DC voltage the sphere gap is firing 50%. So now comes the question of correction factor. As per the standards, first we have to, the formula is equation number 1. U0 is laboratory condition voltage, which is 42.9. Then U I want that today's voltage, so it will be U0 into delta into K. What is delta? Is equation number 3, where B is the barometric pressure. In today's condition, B0 is 760 millimeter of mercury. Then T0 is 20 degree and T is today's laboratory temperature. So we calculate delta. And K is function of delta as well as H. Now what is H? H is related to humidity. How we get humidity? For that we need dry bulb temperature reading and wet bulb temperature reading. So we have this thermometer. We have the aneroid barometer to note down the pressure. Then I have this curve, which is in IS 731. X-axis is dry bulb thermometer reading. Then this curved line, on that curved line, you have the wet bulb thermometer reading. So on the day of experiment, let's say our temperature is 30 degrees centigrade, dry and wet is 25. So take the vertical line from 30 degree and that oblique line starting from 25. Wherever it cuts, go to the y-axis, get the absolute humidity. I repeat, let's say the dry bulb is 30 degrees, so take the vertical line from 30 degrees. Let's say the wet bulb is 25 degrees, so take the oblique line 25 degrees. Wherever it cuts, go to the y-axis, get absolute humidity. What is the unit of absolute humidity? Grams per meter cube. That means 20 grams of moisture per meter cube of air. So typically, a measurement value is given that 42.9 at STP, say dry bulb is 32 and wet bulb is 30, barometric pressure is 756. So delta can be straight away connected as per the previous equation. Then from this, we find H is 29. Then we put this value of H in that equation. That which equation? This equation. So delta is calculated straight away from barometric pressure and temperature, and H is calculated from that curve, and then H and delta in equation 2 gives the value of K. So we find out K, and then U is equal to U0, that is 42.9 into delta into K, so 42.8. So we need that this sphere gap breaks down means 50% breakdown occurs at 42.8 in today's lab instead of 42.9. So every day it will vary slightly depending on temperature and pressure. So what we do? We do an observation that for that particular DC voltage, what that 50% we got. So here you show that 4-time breakdown has occurred, 6-time breakdown has not occurred, but still it is acceptable, which is 4 out of 10 is 40%. So we take that DC voltage as whatever is the correct 50% flashover or 50% disruptive discharge. So then what we say that, let's say for that our voltage is 26 kV DC. That means this 40% we have obtained with 26 kV DC. So we know that the sphere gap will discharge at 42.8 because we applied the correction factor. So we say that 26 kV DC is equivalent to 42.8 kV of impulse at laboratory condition. Second line or second bullet. Or from there we say 1 kV DC is 1.64 kV peak impulse. Now that's the calibration that we have calibrated the impulse generator. So now if I want 100 kV impulse, we just simply back calculated whatever is the DC value required. And then we operate the impulse generator looking at the DC meter, not looking at the impulse output. So we perform the impulse withstand test in the IS731 for an 11 kV pin insulator. The highest system voltage is 12 kV. And for that, the impulse withstand voltage is 75 kV peak. So it should be plus minus 75 kV peak. But then this is at STP. So at today's laboratory condition, what should be the withstand voltage? So IS731 again corrections as per appendix A, we calculate first D here. P is the barometric pressure, TD is the dry bulb temperature. And then, see, from here we get D, and then there is a table D versus K. If you look at this table, you see 0.95 to 1.05. D is equal to K. So you don't require anything. But if D is beyond that, you have to plot this table, and from that plot, you have to find out what is the value of K. And again, you have to calculate H, which is with the help of this diagram. And then there is another curve, for which we get the two correction factors, H plus and H minus. And of course, the H plus is positive impulse, H minus is negative impulse. On the x-axis, you have the absolute humidity. Y-axis, you have the correction factor. So this curve gives you the absolute humidity from the dry bulb and wet bulb thermometer. Same, that value you said 20 is the value. So take 20, go vertically up. Curve A is the positive impulse. Curve B is the negative impulse. So go to the y-axis, get the correction factor. So this is the correction factor then we apply, that U0, that is 75 kV as per standard, multiplied by K divided by H minus. That will be the applied voltage for negative impulse. U0 into K by H plus, that will be the applied voltage for positive impulse. The point to note here is that withstand test has to be done applying both positive impulse and negative impulse, not just one. So we calculate this for a particular value, again 32 and 30. This is the value of delta. How we got it? From this D, and then from there K. So this is the value of D or delta, and 0.95 to 1.05, D is equal to K. So K is also this. From this chart, that is this one, for 32 and 30, the value of absolute humidity is 20 grams per meter cube. Then from this curve, curve A and curve B, positive impulse and negative impulse, I get H plus and H minus. By the way, I must say that there are two types of correction factors you have to calculate. One for this pin insulator and another one I have explained earlier. That is this one. This is for the sphere gap. So first what we have to do, we have to calibrate the impulse generator. For that we use the sphere gap. And for the sphere gap, we do the correction factor calculation using this slide. Then what we do from the sphere gap value, we find out the calibration. That is 1 kb DC is how much impulse. And after that, we remove the sphere gap. After that, only the insulator is there at the output. And then we calculate the correction factor using this procedure. So please remember there are two stages of correction factor calculation. One for the sphere gap, one for the pin insulator. Yes, yes. Achha, for the breakdown, yes. Hmm. Yes, yes. Yeah, calibration is done irrespective of that, yes. But for the testing of the pin insulator, the standard specifically says that you have to do it for both positive impulse as well as negative impulse. There it is very specifically mentioned. So in our lab, what we typically do, let me tell you, we calibrate using the negative impulse for the sphere gap. And then when we go for the testing of the insulator, that we do both for both positive and negative impulse. That is permissible. Tomorrow, I don't think so because I have been informed by the you can coordinate with Suparna ma'am. I think tomorrow there is no class, so please coordinate with Suparna ma'am. I think your class, all the classes are going to be from the next week. That's what I am told. So please coordinate with Suparna ma'am. I don't know. I heard that. That's what I heard. So you please after this, you have to coordinate with Suparna ma'am. She knows it. Yeah. I mean, you can send me an just email, drop an email. So then, very simple that we have already calibrated that 1 kb DC is equal to how much impulse. Then whatever value comes here, this U minus and U plus, this is, remember, this is calculated value. And then we calculate what is the DC value required. So we find that the one is 41.4 kb, other is 50.5 kb. This is for positive impulse and the other one is for negative impulse. So we just change the switch in the impulse generator for negative and positive. And then we just adjust the impulse generator sphere gap, that is the trigger gap, and apply 41.4 kb DC voltage and 55.5 kb DC voltage. And then what is the procedure of withstand? See, impulse is all probabilistic, not like AC and DC. In an AC and DC, if the breakdown occurs at X kb, every time it will breakdown will occur at X kb. But not impulse. If you apply X kb voltage, I have already explained that there is a probabilistic curve and there is a voltage time characteristic. So there is a procedure again given in IS 731 which says that we have to apply 5 impulses, and if there is no flashover, then the insulator has passed. So 5 positive impulse, 5 negative impulse, no flashover, pass. Within this 5, if there is more than one flashover, either in positive or in negative, anyone fail. I repeat, within this 5, if there is breakdown either in positive or in negative, more than one, fail. If there is one breakdown, either in positive or in negative, or both, then 10 more impulses of same polarity has to be applied. That means if one flashover for positive impulse occurs, apply 10 more impulses of positive impulse. In that 10 impulse, there should be no flashover. Even if one flashover occurs, fail. So that is the procedure that we will have to follow. So I repeat, 5 impulses are positive and negative. If no flashover, pass. If more than one in any one polarity, fail. If one flashover in any one polarity or both, apply 10 impulse of that polarity. In that 10 impulse, there should be no flashover. Then pass. If there is one flashover in the 10 impulse, it is fail. So just follow that and we determine the withstand voltage. So we do it through these gaps again. Then we go for the flashover. In this case, it is just the reverse, calculation we do. Now here, we start slowly increasing the voltage, both positive or negative, and find out that exactly what DC voltage the pin insulator breaks down 50%. Remember, this is not the sphere gap. The pin insulator breaks down at the 50%. That means now this is happening at the peak value or the impulse. Let's say this is 60 kV, the second bullet. So we know the calibration, we multiply it. So this is 98.4 kV peak. But now this is the laboratory value. We can't declare the result at laboratory value, or every result has to be declared at standard temperature and pressure. Why? Because then that value can be compared with another test result on another day. Otherwise, you cannot compare because every day the correction factors are different. So here we do the reverse calculation. That means now here we have to divide by K and multiply by H. Previously we knew the standard value, which was 75 kV for the withstand test. So we divided by multiplied by K, divided by H in that case. Here we have measured the value of flashover voltage at the lab. So this is lab condition voltage, 98.4. So we do the reverse calculation. We divide by K and multiply by H and get the standard value. That is uh, the STP value. So this flashover test also you have to do separately for positive and negative. And the correction factor H will be H plus for the positive impulse, H minus for the negative impulse. So in the laboratory, typically withstand test, we show you the entire test, but flashover test takes a long time because we have to adjust the flashover value. So we don't want to run our impulse generator for that long. So probably this flashover test will show, our people will show you for one polarity only. And by the way, we cannot allow you to run the impulse generator because it is a very expensive equipment. So our technician will run it. But I request that whatever I am trying to explain, just try to always see that. And if anything required, just insist that I want to see this thing. Yeah, because it is you who are here to learn, not the technician. So this is the whole experimental this thing that impulse withstand and flashover. So there are, I just give a summary. What is there? One, first you have to understand there is something called 50% breakdown in impulse. In AC and DC, if breakdown occurs at X kV, it is always at X kV. So it is 100%. But impulse, it is probabilistic. So the breakdown occurs at peak only when it is 50% probability. And that can be explained by theoretically through the voltage time characteristics and the impulse wave. Then I have to calibrate it with the help of a sphere gap. So for that sphere gap, I have a standard value of breakdown for a given gap distance. For that, I have to calculate the correction factors. For that, there is a process. Then I find out at what DC voltage the sphere gap is breaking down at 50%. From that, I calculate what is the calibration value. That means 1 kV DC is equivalent to how much kV peak impulse. Once we know that, we go to the withstand test where the standard specifies a value. For 11 kV pins insulator, it is 75 kV peak. But that is at STP. So again, we take into account the correction factors and there is a process. As per that, you calculate the correction factor. Apply it on 75 kV and you get two values, one for positive, one for negative impulse. Then we have to apply the appropriate DC value. We know the calibration, so I can calculate. We apply the DC value for positive and negative polarity and perform the test. We apply 5 impulses. If there is no breakdown, both positive and negative, pass. If there is more than two breakdown in any one polarity, fail. If there is breakdown only once, either positive or negative, repeat 10 impulses of that polarity. If there is no breakdown, pass. If there is one breakdown, fail. So you have to note down this whole process, that is what is happening step by step, and then you declare the result, it has passed or it has failed. Then you move on to the flashover test. Here we go just the other way around. We slowly increase the voltage. In our lab, we will show you an one polarity, let's say positive polarity. And we find out at what DC voltage 50% flashover of the pin insulator occurs, not on the sphere gap, pin insulator. Then that is the flashover voltage at STP. So we back calculate that correction factors and find out what is the STP value of the flashover voltage. And that value has to be declared as the flashover voltage of, let's say, positive polarity impulse at standard temperature and pressure. So this will be your entire experimental procedure, which for this particular experiment you are going to observe. So this is a little bit detailed explanation. I tried to give you the entire thing. Part of it, the generator part of it is already told, I mean, in your high voltage engineering, it was there. I repeated it. But that 50% and all that, probably I don't know whether you have gone through it. Maybe in your third year, slightly it was taught in the measurement part. But this will be in details in this experiment. So this is what I thought that I should give this entire explanation to you well beforehand, so that at least you know that what is the background, which experiment you are coming to perform. And then in the lab, I request you try to see that what are the components, how it is being done, how it is being connected, so that you get a first-hand knowledge. Good. Now, if you have any question, anything, if you want to ask me, any student? No, peak voltage at which the breakdown is occurring, not withstand. Yes. Ha. See, I will show you like this. You can see this one. See, this is, again I repeat, this dotted line. See, these are all experimental. Huh? This is that experimental. This is nothing theoretical. This is all done through experiment and not in one lab, multiple labs in different parts of the world. This is a very extensive work done. Long time back, this is nothing new. So this dotted line is called the voltage time characteristics of breakdown of what? Air. So if you apply, I mean, if the breakdown occurs at very small time, you require a higher voltage. If the breakdown occurs at longer time, you require a lower voltage. So you can see this curve. But impulse voltage is fixed wave shape. That peak will always occur at 1.2 microsecond. So these are the typical impulse voltages, where peak is all occurring at 1.2, but the voltage is increased or decreased. But this dotted line is cutting the impulses at different places. So when it is 50% probability, then it is cutting at the peak. That means If the breakdown is 50%, I can say confidently that it is occurring at the peak. Why I am bothered? Why I am bothered about peak? Because in impulse we want to know the peak value. We are not bothered about RMS value or etc. etc. So from this we are sure that the breakdown is occurring at the peak. If it is less than 50%, you can see that this dotted line is cutting the impulse on the wave tail. If it is in more than 50%, you can see the dotted line is cutting on the wave front, but not at the peak. That's the explanation from the physical explanation of the whole thing. Any other student, anything? Okay, in that case, then let us close this session. So thank you very much. You can log off then.
So, could you please share this presentation with us in case we need to refer it?
I see. Okay. Okay, then I will have to just do something because everything is not needed for you in this one. I will just edit and I will send it. Okay, that can be done. Yeah.
Thank you, sir.
All right. Good night.
Good night, sir.